no one knows me real good. I don't know you very well. What's your name?
Trevor.
Trevor. Were you in our class last semester?
Yeah.
Yeah, you looked a little familiar. Well, I'm going to talk about a very slow series that I was responsible for discovering or inventing. I like to think I invented it and then discovered many of its qualities. Its quantity and many of its qualities. So it's called the MRB CONSTANT.
Oh, sorry.
That's good if you.
Well, let's leave it like that.
Okay. And by the way, when the lights come back on, I got something for you to look up when I'm done or after the class. MRB CONSTANT Records, and you'll find out what I spent 8 years writing. That's a book. It's size of a small book. It's the size of a booklet, about 60 pages or so. Okay. So anyway, I've been known for being crazy all my life, especially after I got out of the Marine Corps. A crazy person can form an original idea. They're good at it. From what I've heard, they're good. From my experience, we are good at it. But only by being humble can the idea be put to practical use. I invented the MRB CONSTANT. Let's see here. Let me read this for a second, because I spent some time writing it out. I'm known for discovering, or rather inventing, an attractive quantity that's been read in Wikipedia 2 million times. Does that then a mathematician make? Not entirely, really insane. It's 1994, and as you wouldn't treat a dog, the absence of invention and poverty of purpose shackles my hand to remote control. Here I lie, spellbound. Sounds and images cycle before me. Faster and faster, the stations run their course at an exponentially increasing rate. As a condemned prisoner awaits the throe of the death which my mind entreats, haste the time when sleep silences reason. Then, sudden as coronary, my aching heart replies, is this all there is in life? One miserable TV show after another, bed, work, one miserable TV show. Of what good to the world is this mind? The deceased care not, they have no abated hope, grieve not, and have no need of destiny. I do. No more, frantically wails my dying heart. So, then as strange as it seemed, I started writing out the powers of 2. I was good at math in high school. I remember some of the powers of 2 by memory. And after 40 years, I still remembered some of them. So I wrote down 2 times 2 equals 4, 2 times 2 times 2 equals 8, etc. As if I lost my wandering mind and found a working one, I did this. Look at where it says from, and then I'm going to read it a certain way. From 1 squared equals 1, I got the first root of 1 equals the 1 squared root of 1 squared. Read the next math while I read it. From 2 squared equals 4, I got the 4th root of 4 equals the 2 squared root of 2 squared. Again, from 3 squared equals 9, I got the 9th root of 9 equals the 3 squared root of 3 squared. That might seem hard to understand, but look what happens if we put that in general. Again, read the math while I read the next line. From n times n equals n squared, I got n squared root of n squared equals the n squared root of n squared. Is there an echo in here? Thus, I went from squares to roots. So, trying to form an original statement, I asked, what if I were to add them and all other principal nth roots of n together in an alternating series and call it the root constant? I asked myself, what's 1 minus the square root of 2? So I said, well, next would be 1 minus the square root of 2 plus the cube root of 3. 1 minus the square root of 2 plus the cube root of 3 minus the fourth root of 4. Still curious, I tried to summarize what I was doing and considered the sum's additive inverse, in other words, reverse the signs. What if I go into the 10th root of 10? I got 0.3 such and such. Until the 100th root of 100, got 0.2 such and such. Until the 1000th root of 1000, with my computer, of course, I got 0.1 such and such. And until the previous number, I got exactly one less, like 9, 99, and 999. I did it, I said. I invented a new mathematical concept, so I told everybody. I didn't care how much they knew, they must know this. My peers, of course, all said I was crazy again for this. But without missing a beat, I went on and started writing mathematicians. The World Wide Web was new back then, and professional people didn't mind checking their email, and there wasn't as much spam. Without even asking my permission, they simply began publishing the Marvin Rayburn's constant, MRB constant. Wow, I haven't come back to Earth since. So what exactly is it? I described it a little bit already. Like I said, it's a real slow convergent series. It started out with a divergent series. I found the MRB constant, MRB, by adding Grandy series to the following sum. You'll find out what the Grandy series is in a minute. So here's this divergent sum, -1 to the k times k to the 1 over k. Here's how you spell it out, -1 plus the square root of 2 minus the cube root of 3 plus the square root of 2 or fourth root of 4, same thing, minus the fifth root of 5 plus the sixth root of 6, blah, 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 on to whether it's plus or minus 1 to the 1 over n. The limit is n goes to infinity of that. The sequence of its partial sums has 2 limit points, with an upper limit point known as the MRB constant. That's when you stop at that even number, like 10, 100, 1,000, a billion, trillion, a Google. When you stop at even number, you get an approximation for the MRB constant. And there's many formulas for the MRB constant, many series and many integrals. This is what I call the sum prototype for the series. Notice what we got here, that the divergent series is still here. But I added 1 to a term, subtracted 1, added 1, that plus 1, minus 1, plus 1, minus 1, onto infinity is called the Grandy series. So I just added the 2 divergent series together and got a convergent series. Equals CMRB, the MRB constant. Here's how it's written out. -1 to the power of n times n to the 1 over n minus 1. It can be proven to be convergent through simple calculus. I prefer this proof because I understand it. We use the squeeze theorem and plotting to see that the qualification for the Leibniz criterion, or alternating series test, is satisfied for the MRB constant n. Look here where it says CMRB equals, and then we got the sum of 1 to infinity, which equals the sum of 1 to 3, and there's a reason for this, breaking it up like this, and the sum plus the sum of 3 to infinity. By showing, we're going to show that a sub n equals n to the power of 1 over n greater than 0 is monotonically decreasing for n greater than 3. That's why we broke it out, because it's increasing before then. And has a limit as n goes to infinity of 0. Of course, the first one converges, and the sum of 2 convergent series converges. So I assigned the expression to a sub n, and I wanted to find out what the critical points were. So I said solve. It said E. I said reduce, another more expensive operation. It said E. So I plotted it from 0 to E. And of course at 0 it's undefined, but the rest of it shows. Then it goes out to E to the 1 over E minus 1. And then I said, well, I'm going to plot it from E to infinity. And Mathematica after 13.0 lets you plot to infinity. So I plotted from E to infinity, it went down. That didn't prove anything. Still didn't know, well, I did know, but I didn't prove that the limit as x goes infinity is 0. Mathematica says it did, But I didn't want to trust mathematics, I want to find out for myself. So I found a series for a sub n, the first 6 terms. I took the normal, in other words, that takes away the O, the big O term. And I noticed there's, of course, 6 terms. So I maximized n to the log of n to the 1 over n. You see that's in each of these terms, log n over n is in each of these terms, and then it's raised to a power and divided by a factorial. And the biggest it ever gets is 1 divided by e at e. So, right here is where my mouse is the limit as n goes to infinity of n to the 1 over n minus 1. And I'm sure it's greater than the log of n over n as n goes to infinity. Greater than or equal to, that is. And that's greater than or equal to 0. Well, what about the other side? Is this really 0? So I asked whether it's less than what the maximum this expression can be as you go to infinity. The maximum is 1 over e to the power of x divided by x for factorial, x times, and the limit is x goes to infinity. And I just assumed it equals 0, so I put equals 0. And it was true. Thus, the limit is n goes to infinity of n to the 1 over n minus 1 is 0. So we have shown by plotting in the squeeze theorem, or sandwich theorem, that Leibniz criterion alternating series test holds. As we have seen, for n greater than 1, the derivative of 0 is only at e. There are no more critical points for the plot to cease to decrease. Thus, a sub n is monotonically decreasing for n greater than 3 and has a limit as n goes to infinity of 0. Finally, that first sum from 1 to 3 of a sub n converges, obviously, and the sum of 2 convergent series converges. Therefore, the series is convergent. You can find proof of the Leibniz criteria, although you've seen it in calculus, in Wikipedia. So there's another, that was what I call the prototype sum of the MRB constant. My first sum, the prototype. That's what I call the prototype sum. Well, there's another sum that's more efficient. Like I said, the MRB constant is really slow. Oops. I just want to see if I got something I want to say here. Written down. It's really slow to converge. This Dirichlet eta formula for the MRB constant converges much faster. I don't know why that's going up. Something's wrong with the mouse. Try not to use the mouse. The Dirichlet eta function sum is much faster. It was discovered by Richard Crandall in 2002. Richard Crandall was Apple's chief cryptographer and chief scientist for a while. We have the following computational scheme using the zeta variant called Dirichlet eta. He said, remarkably, he was talking about the MRB constant. Remarkably, if we look at our voluminous list of zeta variants, he lists all of them and forms a way of getting all of them from each other. We use a series for k to the 1 over k, which is e to the log k over k, and obtain at least formally a joule of an expression. B, or the MRB constant as he called it, is the sum, the negative of the sum of negative 1 to the m over m factorial times the nth derivative of eta m at m. a little tricky, but that's how it's written out, which series actually converge rather quickly. Take a pause there. For the MRB prototype sum to converge to n digits, it takes 10 to the n plus 1 iterations. So like we saw before, when we summed up to 1,000, we only got one accurate digit of the MRB constant, the 0.1. But it averages out, like I said. So in other words, to get 9 or 10 digits, it takes billions of terms. It's not the slowest series in the world. It's the slowest one that I know of that has a lot of purpose to it. You can make up one that goes way slower. There's one made up, and instead of n to the 1 over n minus 1, it's a log of n. It's very slow. You might have to take a Google terms to get 10 or 12 digits. And then you just throw in another log, 3 logs. It might take a Google Flex terms to get 10 digits. I don't know. So you can make them up as slow as you want. There's another formula for B, and that is the sum of C sub n, where C sub n is this little sum, for C sub j, C sub m, C sub m over m factorial times the nth derivative of eta 0. And he says it may be lucrative to use that formula. He died before he could find out. I've got some ideas how it is lucrative to get more digits out of it, quicker with less computational effort. Like I said, the nth derivative of eta m and the nth derivative of eta 0 denote the derivative of the Dirichlet eta function at m and 0 respectively. Here's a formula to get the C sub j's real easy. They start at -1, -1, 2, 9, 4, -93, -414, 49, 1,088. They get bigger from there on. Here's a little proof of it, which is kind of fun. So we want to compare n to the 1 over n minus 1 to these Dirichlet eta derivatives. Well, as he said, the n to the 1 over n is exp log n over n. So on the left side we got that, and of course plus 1. So this equals the exp log 1 over 1 plus 1 equals a log of 1 over 1 in series form. In other words, a log of 1 squared over 1 squared 2 factorial, and so forth. Similarly with 2 and 3 and so forth. And so this first column is the first derivative of eta sub 1 over 1 factorial. Eta sub 1 is actually undefined, but there's a value you assign to it. But eta 2 and eta 3, and the derivatives of eta 2, eta 3, and so forth, they are all defined, and you can find them through pure math, regular math. Now there's an integral. You don't have to rely on a sum or any of those sums, or there's other sums too, but those are two distinct, definitely non-trivial and distinctly non-trivial sums. You don't have to rely on a sum. You can take an integral to get the MRB constant, which is much faster. So I took the Abel-Plana formula from Wikipedia, and I just spelled it out. See where it says equals MRB, the sum, you put the sum, the prototype sum at the end there. It equals, according to the Wikipedia, S sub it minus S sub negative it over e to the 2t minus 1 times I, plus the integral of that kernel, the same kernel that's in the sum. that equals the sum. So I did that and showed that it works. So we had, here's the kernel if you go from 0. The Abel-Plana formula works from 0, not from 1 to infinity. So here's the kernel if you use from 0, an index from 0. Let that be f of x, let g sub x be part of it. And sure enough, it works. And so what we have here in the first yellow, right here, in yellow all the time here, is what you call the integrated analog of the MRB constant. It's the MRB constant's kernel. You erase the sum sign, the sigma, and you throw a integral from 0 to infinity and a dt. The integral sign before it, the dt at the end of it, and you've got the integrated analog of the MRB constant. But when we added the integrated analog to this function, we got the MRB constant, or an integral that equals the MRB constant. And if you simplify it, you get this, the imaginary part of 1 plus it to the power of 1 over it times the cosec, how you pronounce it, of pi t dt. That's an integrated form of the MRB constant. So you notice the difference. The analog, something that's, you can picture what an analog is, something similar, something that follows the same pattern, or in this case it has the same kernel, the same expression. As I said, n digits of the prototype of MRB constant converge after about 10 to the 1 plus 1 iterations. However, if you integrate, and you notice this has got an I in it, so we can change this. There's a way to change this. I'll show you what it looks like when you do. And integrating over I, every 75 I, so like from 1 to 75 I, yields 100 digits of the integrated analog, or M2. And then from 75 to 100, right here, from 1 to 75I gives 100 digits. From 1 to 150 gives 200 digits. From 1 to 225 gives 302 digits. To 300 gives 400 digits, and so forth. That's the integrated analog. But the same thing's true about the MRB constant formula. The integrated analog is here, integrating from 1 to such and such I. To get the actual value, you go to infinity I. So see, there's a kernel that's in the sum. EXPI is same as -1 to the x. And here's that integral that's the same as, gives the same value of the MRB constant below it. And it converges at exactly the same rate. And that's it.